Alright, here's a problem that doesn't really come up that much in Folland. At least the stuff that we're talking about is these coset things. Feels kind of algebraic, so like if you're an analyst you might be like a little put off by that, but stuff is actually kind of cool. And even though we don't really talk about it that much, like this kind of stuff in particular, this is kind of like whenever we're dealing with measurable sets in the first place, we're kind of quotienting out by like sets of measure zero in a sense, or like functions, like you consider not functions themselves but classes of functions which are equal almost everywhere. And so we're kind of dealing with cosets in the background. We're just kind of brushing that detail under the rug. So anyways, here's our thing, and then first we want to prove that this is a subspace. So let x and y be in script m and lambda in, say, k. And remember, k is either the real numbers or the complex numbers, whatever. I think I had a professor say once that it suffices to consider any field which contains the real line as a subfield, but whatever. And by suffices, I mean like all this stuff works for such a field, but it doesn't really matter. But anyways, we want to prove that this thing has norm 0. And so this is a semi-norm, so this is going to be less than or equal to, we can break the thing up, but I'm just going to, instead of doing plus and then lambda y norm, I'm going to automatically bring out this lambda here. But x and y are both 0 norms since they're elements of script m. So this is 0 plus 0, which is 0. So this lambda y is an m, and thus script m is a subspace. Now let f, I'm just going to call it f, so we have a name for it, and then to prove f is a norm on x mod m, let's let x and y be an x, and here let's also let lambda be in k again. And we want to prove that the sum of two things is less than or equal to the norm of the sums is less than or equal to the sum of the norms, and that you can bring the constant out front. And this is basically going to follow from the fact that this thing is a semi-norm. That's really going to be the key here. Then let's see here. Let's put out a new line, make this look a little neater. It's plus m plus y plus m. Well, in terms of cosets, this is just the coset, the x plus y coset of m, and this is equal to norm x plus y. And again, since this is a semi-norm, this is less than or equal to x plus y. Then of course the other thing is f of lambda times x plus m is, again, because of how cosets work, you can bring the lambda in. This is lambda x. And then again, you just do the thing. This is kind of weirding me out because my flux just went on, and so the screen just dimmed. Hopefully that, I don't think that catches on to the screen captures, but yeah. Just weirded me out a little bit because like you're writing and then you're just like, oh wait, something weird is happening. Oh, it's nighttime. So anyways, we want to prove that's a norm, not just a semi-norm. So let's suppose this equals 0. Then, well, what does that mean? Other than that boy needs therapy. it means that norm x is equal to 0, i.e. this is contained in script m. So if x is in script m, then x plus m is equal to m. But now here what you have to keep in mind is that script m is the 0 element of x mod m. Because if you were to take 0, because the 0 element of this would be, you take the 0 in here and add m to n, that just gives you m. And so we've proven that if f of a coset is equal to 0, then this coset must be the 0 coset. And that means precisely that f is, well, that means precisely that f is, I forget what that property is called, but that combined with the with these two things tells us that f is a norm. And so this is kind of cool. We took a semi-norm and we modded out by all the things whose semi-norm is equal to 0, and you get a norm. And if you think about it, that's kind of what should happen, because you're modding out by all of the things that keep your semi-norm from being a norm. So in that sense, this is kind of a neat problem. And there you go. We've completed the proof.